And the next talk is by Greg Tyrrell of Oxford University on new lower bound.
Hopefully it's all fine. So thank you everyone for your patience, and particularly thank you to stepping in at short notice. So funnily enough, what I'm going to be talking to you about today, new lower bounds for CAPSET, is actually very related to our previous talk. In particular, the original research on lower bounds for CAPSET also came out of thinking about error correcting codes and projective geometry. Unfortunately, I won't really be talking about any of that because my motivation, for reasons I'll explain in a second, is from a completely different branch of maths. So yeah, let's jump into it. So as I say, so my motivation comes from a very different area. So let me just talk briefly about the sort of problems that I think about and why I think this is interesting. So, so I enjoy two things. Well, I enjoy many things, but particularly two things in maths, which is number theory and combinatorics. In particular, I like asking sort of combinatorics type questions about number theory objects. So one such example is given here. So if I take a bunch of integers, what's the biggest subset of them I can have that has no arithmetic progressions? So by an arithmetic progression, I'm talking about like x plus d, x plus 2d, and so on, like an equally spaced sort of sequence. And you might say, is it possible always to pick, say, 1/100th of the numbers and have no progressions, or 1,000th, and so on? And a very well-known result of Roth says, no, that's not possible. As you increase sort of the length of your interval, the biggest progression-free set can only take up sort of 0% of the interval. I won't say too much more about this because there is a talk on this theorem tomorrow, and I don't want to steal their thunder. But this is, as I say, a very important question in additive combinatorics. It's also a very hard question, and in particular, sort of getting good sort of quantitative results on how big a progression-free set in the integers can be is very hard. There was a breakthrough about a month ago that everyone was very excited by, and even then, it's a really quite a big deal. So as mathematicians, one of the things we like to do when questions are quite hard, well, the first thing we like to do is just kind of moan about it. The second thing we like to do is ask a slightly easier version of the same question. And this is where the idea of cap sets come in. So rather than working over the integers, for the rest of this talk, I'm going to be talking about objects called cap sets, which are objects in F3 to the n, and I'll explain what that is in just a second. So a cap set is a subset of F3 to the n where no distinct triples of elements adds to 0. So by F3 to the n, what I actually mean is it's the vector space of dimension n over the finite field F3, or more concretely, you can just think of it as vectors of length n where every coordinate is a 0, a 1, or a 2, and we're adding them together mod 3. And the cap set problem says, what is the biggest size of a cap set? It's the sort of most basic, obvious question you can ask about this. So we're looking for sort of the biggest set where no 3 elements add to 0. And the connection to the previous slide is that, in fact, a cap set is exactly the same with a progression-free set. So there are no solutions to this x plus y plus a equals 0 if and only if there are no non-trivial arithmetic progressions. And the connection to the previous talk that I mentioned sort of initially was also, this is if and only if there are no 3 collinear points, which that's not the angle that I'm coming at when I'm talking about this problem, but lots of geometers, finite geometers, are actually interested in this problem as well. Okay, so that's a cap set. So this is a sort of finite field version of the sort of more complicated question over the integers. So we're looking for progression-free subsets. Now, the reason that it sort of makes sense to ask it over a finite field versus over the integers is that often working over a finite field like F3 to the n, we have a lot more tools at our disposal. In particular, F3 to the n is a vector space, so we can do linear algebra, and we can't do that in general over the integers. There's lots of sort of extra technicalities that are introduced when we try and think about problems in the integers. So this is a very well-known sort of meta strategy in additive combinatorics, which is find a really hard problem in the integers, put it into a finite field instead, see what happens, and then try and translate some of our ideas back. And indeed, that is exactly what has happened on this problem. So all of the sort of breakthroughs and results on this question of the biggest progression-free sets in the integers have made use of various results on this cap set problem. So here is a brief history of the cap set problem. So the best known upper bound was proved by Ellenberg and I think it's pronounced Gieswit. So they proved that no cap set can be bigger than 2.755 to the n in n dimensions. This was a big breakthrough. It answered a question of Terence Tao and Tim Gowers and many other very well-known, very famous, very clever people. And in particular, it was notable because their proof method was beautiful and short. It was like a 4-page paper, and it's essentially linear algebra with some baby algebraic geometry. It's very nice. So that's the upper bound, and the corresponding lower bound, which is the focus of this talk, is the sort of world record in that is my own recent result, where I've proved that in n dimensions, there's always a cap set of size at least 2.218 blah, 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 to the n. So you'll notice that obviously there's famously 2.75 and 2.218 are not the same number, but our two bounds are of the sort of same shape. They're both exponential, and they're not a million miles away. So we're doing quite well on cap sets. And I'll say a little bit about at the end about sort of my thoughts about sort of narrowing this gap further. But now let me tell you, how I obtained this new lower bound. So it's worth just pointing out. So, to find an upper bound for this problem, you have to show that sort of anything that is at least this big can't possibly be a cap set. And it's the kind of existence or non-existence proof. The lower bound is a sort of philosophically very different argument, and it amounts to basically giving a construction saying here is a big cap set in any dimension. So certainly this is at least a lower bound because I can make a cap set this big. So it's a much more sort of hands-on version of the problem. And what we're interested in doing is trying to cook up some large cap sets. So the basic construction for a cap set is to take two cap sets and then stick them together. So what I mean precisely by that is to take their direct product. So this is the first lemma here. This is actually very easy to prove. And once we've obtained this result, we then get what are called exponential bounds for free. So the second lemma looks like it's a very technical, complicated lemma. It's really not, and I'm saying nothing clever here. Basically, all I'm saying is that if I've got any particular cap set, I can take direct products of it with itself as many times as I want, and asymptotically, sort of for very large dimensions, that gives me a good lower bound for the cap set problem. So the sort of the headline here is that the whole point is that we only need to give one good construction of one specific cap set, and then we get asymptotic exponential bounds for free. So again, this lemma looks quite technical and clever. I promise you it's actually really not. It just looks like it's some sort of statement in analysis. I put an epsilon in there just to make it look a bit more clever. Let me briefly mention the sort of previous work on this problem. So as I say, so as is usually the way with all research, right? The way I did this was first by going to look at the previous research in this problem and working out what they'd done, how they got their result. So a guy called Edel introduced this idea of an extendable collection and an admissible set. I haven't put the sort of precise definitions up here because I don't think they're particularly illuminating, but essentially what Edel did is he takes the direct product construction and then sort of works out a way to sort of twist it, make it a little bit better. Now, you have to be quite careful because you can't always perform this twisted product and still have a cap set, but under sort of particular conditions on the cap sets you start with and the way you combine them, you can get a cap set. So in particular, he introduces these definitions of extendable collection and admissible set. So an extendable collection is a bunch of cap sets that satisfy sort of particular structural conditions. And the best example we know is some things in 6 dimensions. And an admissible set is a kind of combinatorial object that tells us how we're going to combine our cap sets. And then this sort of the main result of Edel is that if we've got an extendable collection and an admissible set, we can put them into this recipe and out pops a bigger, better cap set. And in particular, this cap set in general can beat the sort of direct product construction. So you can get a sort of better lower bound than you would just by performing the direct product. And so for the last 20 years, that's been the state of the art on this problem. And Edel's construction is quite complicated. And in particular, Edel's working over projective geometry, and he's talking about all of the things that were sort of mentioned in our last talk, and I find those quite confusing. So sort of my first job when I was thinking about this problem was to take his paper and sort of translate it into language that made sense to me, which I have now done. And then once I did that, I was able to try and sort of see, could I put in some of my own ideas and take this further? And the answer is yes. So let me tell you now about sort of what I did to improve this, and sort of how I managed to get the world record for myself. So the first thing I did was I came up with a new construction. So I sort of called this a meta extendable construction, which is a sort of little joke. But basically what I did was I took the previous sort of extendable construction of Edel. I came up with a new construction that is philosophically quite close to his construction, but rather than producing big cap sets, it produces big admissible sets, which, if you remember, they're the ingredients that go into making big cap sets. So I kind of sort of took this upper level, and I proved this lemma, which again basically just says if I take a meta extendable collection of meta admissible sets, I get a bigger admissible set. So this allows me to get sort of better ingredients for the recipe than Edel had. So that's the first thing that I did. I say, how did I come up with this? Well, I thought about it for sort of 3 months and tried lots of things. And in the end, the sort of hypotheses and proofs kind of came out. In particular, I sort of did it backwards, where I worked out the sort of result I wanted to prove and then worked out what kind of hypotheses I might need. And I came out, as I say, with this new construction to allow me to sort of get better ingredients. So I'd liken it to, you can imagine if you're trying to make a cake. Edel's given us a nice recipe. He says, get some flour and some butter and some sugar and blah, blah, blah. And what I've been able to do is work out sort of a way to get some sort of better, more high quality flour to then make a better cake, putting it into the same recipe. And so this is all well and good, but it's all, saying I've got a new construction is fine, but I need to have some ingredients to put into my new construction, right? In particular, I want to find some new admissible sets, and I want to find some new sort of objects to put in to construct my big cap sets. And this is where the computational techniques come in. So I use what's called a sat solver, which I'll talk about in just a second, and lots of Python. So I'd never heard of sat solvers before, so it was very interesting to sort of learn about them. I didn't have a lot of experience with coding before as well. Luckily, the interest in the code, what the code might look quite complicated, actually all the sort of difficulty is in the sort of mathematics behind it. The code itself is sort of not particularly complex, and all the code is publicly available. So if you feel like you are really bored and want to spend some time looking at some code, I've got a bunch of these scripts available, which I used in my work. So what I'm really quite excited to talk to you about is the sat solver. So it's not obvious why all of a sudden I've gone from talking about number theory to talking about Boolean satisfiability. So this is a sort of problem in logic. But let me explain why this is helpful. So the Boolean satisfiability problem says that given a propositional formula, which is basically just sort of a logic formula, so like something written with just like implications and ands and nots and negations, and conjunctions and disjunctions and so on, like a purely sort of logical formula, we want to know, can we ever satisfy this formula? Is there a way to make each variable true or false so that the formula overall is true? And if that is the case, then our formula is what we call satisfiable. Now, this is a very hard problem. It was actually the first problem to be shown to be NP complete. But lots of people are very interested in this problem. And in particular, lots of people with lots of money and lots of resources are very interested in this problem. So there are some very good algorithms trying to solve this problem. And so the way you can try and sort of use one of these what are called sat solvers is you take the problem that you're interested in, which is a maths problem, you kind of translate it into sort of logic speak, stick it into the sat solver, it goes and thinks about it for a while, comes back to you with an answer, which you then translate back into a solution to your problem. Now, why have I used sat solvers? Well, the reason I started trying to sort of come up with my own objects for my construction and write some code myself, and it became quite quickly obvious that what I was doing was really just reinventing the wheel, and my code was very inefficient. And actually, a better use of my time and energy was to try and translate my problem into a format that these already existing algorithms could understand, which are much, much faster than anything that I could come up with. So that's why I sort of took this detour into stat solvers. Now, it was quite hard to use a stat solver, but the good news is that stat solvers take a very specific sort of format for their input. So in particular, stat solvers use something what's called a conjunctive normal form. So a conjunctive normal form means that you've got clauses that are all joined by ands. So the clauses are joined by ands, and each clause itself is a bunch of ors. So it might look like, for example, A or B or C, and A or B or D, and B or D, and so on. And it's a theorem that every single propositional formula can be rewritten in conjunctive normal form, but it might in general sort of be exponentially more complicated. In particular, if I want to try and find an admissible set, I can rewrite the hypotheses of an admissible set in terms of logic speak. And if I try and translate it to conjunctive normal form, that's going to take me ages, and I really, really don't have the time, energy, or paper for that. What I do have is a computer and some very basic Python knowledge, and an ability to go on Stack Exchange and look up how to use Python, which is exactly what I did. So Python sort of generated this logical formula for me. So I worked out a way, I just give it the sort of the parameters I'm interested in, and it works out sort of this conjunctive normal form on my behalf. So it kind of, as I say, it exponentially increases the difficulty of the problem. So I wanted to find a set of 330 vectors, and then the sort of logic formula behind that was something with about 762,000 variables. But the good news is that once it's done that, stat solvers are then very quick. So the difficulty was in translating my problem to computer speak, and once I'd done that, it was kind of away and fine, and then translated back to me in happy days. So then that's exactly what I did. I gave my problem to the computer, and it gave me back some nice ingredients, and I stuck it into my new construction, got some even better ingredients, and then put it into the old construction, and then came up with a new answer. So kind of brief summary of what I did. So I used my stat solver to find better admissible sets. I used my new construction to use my sort of better objects from the computer into my new construction to find even better objects. And I use this sort of twice better object in the original construction of Edel to get a better bound than he could. So I guess it's kind of like, you know, if I'm making a cake, and not only have I gone and bought some better flour, I've also now got a better whisk to use in that as well. Now, I don't think my bound is the correct lower bound. I think it's possible to do better. And in particular, I believe that this bound of 2.233 to the n is possible, for reasons that are sort of a little bit too long to explain here. But essentially, if I could prove the things that I was trying to find with the computer, if I could prove that they exist in generality, which sort of my, I guess, experimental results, my heuristics say they should do, if I could prove they always exist, then I could get this bound. Unfortunately, I don't know how to do that yet. I'm working on it. In particular, I've thrown a lot of sort of quite high-powered probabilistic combinatorics at it, and nothing's cracked yet. But fingers crossed. So yeah, that is new lower bounds for cap sets. Hopefully, that's a nice insight into what it means to do research in pure maths, and you know how even a lowly undergraduate such as myself can come up with a new answer to a problem that people are interested in. Yeah, thank you very much for listening to me, and thank you again for your patience in my technical difficulties. I would be pleased to take any questions for a couple of minutes. I think there are a couple in the chat, maybe.
Thank you, Fred. Yeah, there's a question in the chat. What resources would you recommend to learn more about stat solvers?
It's a great question. I honestly can't say that I really know. What I did was I Googled stat solvers and just read sort of whatever came up. In particular, the sort of workings behind stat solvers are very complicated and I really don't understand. I would say the best bet is probably to try and find a maths paper that uses stat solvers and see how they explain it, rather than listening to how the computer scientists talk about it.
Thank you. And another question in the chat: how do we use a function of the 3 elements? Why not a different number of elements?
Fantastic question. Thank you so much. So the reason for that is we want to make our problem as simple as possible. So the shortest non-trivial arithmetic progressions are of length 3. So if we're working mod 3, then we don't have any length 4 progressions, because if we have x plus d, x plus 2d, x plus 3d, well, x plus 3d is just x because we're working mod 3. So we want to kind of find the simplest version of the problem that's interesting. So that's why we work mod 3. You can ask this question about, anything at least 3, but the reason we go for 3 is because it's the easiest non-trivial version of the problem.
There are more questions, but we're running short of time, so I suggest the questioners find you in the breakout room in the networking session. So thank you for Fred for that very nice talk and in difficult circumstances. And thank you to all 3 speakers today for an excellent session.